So this is my final part of my exercise. And here, now that we've done some toy like micro benchmarking, we want to represent some real systems, NVIDIA's DGX2 pods and Google's Cloud TPU as an example, and also represent real workloads like vision model VGG16 and language model GPT-3 and compare those results. So we'll do the very same thing. We will get some system and try to write the network and system info file regarding it. So I'm showing the NVIDIA's DGX2 architecture here. So in the first dimension, each DGX2 has 16 V100 GPUs, and they are connected via NV links and NV switches. And then these DGX2 boxes, multiple boxes, can be scaled out using 100 gigabit Ethernet. And that 100 gigabit Ethernet bandwidth is shared per every 2 GPUs. So per each GPU perspective, the effective bandwidth is 50 gigabits per each GPU. So the first dimension becomes NV switch dimension, and each NV link is having 25 gigabytes per second bandwidth. And as you can see, per each GPU, there are 6 NV links being used. And then this GPU can be scaled out using 6.25 gigabytes per second effective InfiniBand bandwidth. So assume we want to scale out this DGX2 across 16 such boxes. Now this dimension is not 1D anymore, this is 2D. And because the topology is first dimension NV switch, then the second dimension InfiniBand switch, the topologies for each dimension is switch. And the first dimension has 16 V100 GPUs. In the second dimension, we are scaling out 16 boxes. That's why it becomes 16. And if you multiply them, we have total 256 GPUs. And the link per first dimension, we had 6 NV links per each dimension. But the second dimension, we only have 1 InfiniBand link. That's why 6.1. And the link latency for now, just set it to 500 nanoseconds. But the link bandwidth, I just set the correct number, 25 gigabytes per second for each NV link, and 6.25 gigabytes per second for the InfiniBand switch. And again, because new topology has been created, now I'm also creating the new systems info file. Here, mostly things stay the same, but the all-reduce implementation, now because it's 2D topology, we want to use hierarchical all-reduce algorithm. And because all their first and second dimension are both switch, we want to use halving doubling, 2D halving doubling algorithm, because halving doubling is the most suitable topology reflective for switch topology. So this wraps up the DGX2 representation, and this is Google's Cloud TPU representation comes in. So Cloud TPU is nothing but a 2D torus connecting 16 by 16 TPU version 2, and all the links shown here is called inner core interconnect, which is on their paper having 62 gigabytes per second bandwidth. And if you zoom in each TPU version 2 perspective, there are 2 links going out for per X dimension, and there are also 2 links coming out for the Y dimension. So in total, 4 links per each TPU. So using this information, we just create another networking profile. It's still 2D topology and 2D torus, which is in other words like 2D ring topology. And the size was 16 by 16. And the link per each dimension is 2 and 2, so in total 4. And their link bandwidth is equal 62 gigabytes per second. And again, like new topology file has been created, so we create corresponding systems info file. Again, nothing changes, but the all-reduce implementation. But unlike the switch one, this is ring. And for ring topology, the best collective algorithm is ring all-reduce. That's why we're using 2D ring hierarchical algorithm for TPU, Cloud TPU architecture. Now the systems and networks has been created. The final one remaining is representing workload. And just to recap, each workload consists of layer information. And for layer information, and like the bottom line, we need 3 information: the compute time, and the communication type, and the communication size. So this is one example of representing VGG16 workload. So I just only zooming in the first layer, and here I want to first get the computation time. So VGG16 first layer is nothing but a gem operation, and the size is shown here, about 50K times 27 by 27 by 64. And we just do the math. It has about 173 million total operations. And I also just go inside the TPU white paper, and they say their nominal performance number is 46 teraflops. So if you divide this total number of operations by the TPU version 2's performance, I roughly estimate the total communication time is about 3,400. But this is just one way of estimating the compute time. You can use your own GPU simulator. You can also run the actual workload for a while and then measure the actual GPU's computation time. Or we also offer you this workload generator using ASTRA-sim, a systolic array simulator that our lab has been created. So the bottom line is you can get this computation number offline and plug in to the ASTRA-sim workload info file. Then the communication size, because this is simple, VGG16 is a simple vision model, we only use data parallel. And the thing to communicate is this kernel. So I just show the kernel size here is 3 by 3 by 3 for the 3D matrix. So the number of elements in total is about 1,800. And assuming 2 bytes are taken per each element, the total communication size for this first layer is about 3.5 kilobytes. So using this number, we can create the first line of VGG16 workload. The computation time we just estimated is about 3,400. And because this is pure data parallel, we don't have any communication for forward and input gradients passes. But the weight gradient pass, we have all reduced communication, and the size is about 3.5 kilobytes. The compute number here, this 3,400 nanoseconds, is estimated using the number of TPU version 2. But on the 300 paper as well, they say their teraflops is much higher, 112. So again, we can create a new workload file just for 300. But just like we did with the communication scale, we also offer this computation scale as well. Because 300 is much faster than TPU version 2, it only takes about 0.41 computation time of TPU. That's why whenever running the VGX2 boxes, we can still use the TPU's workload file, but set the compute scale to 0.41. That will automatically scale the compute time as well. So till now, we have generated the network and system info file for both DGX2 boxes and Cloud TPU, and we just represented the VGG16 workload. Now we can run it. So we can go to this exercise 3 folder and run the script. So yeah, before running the actual thing, let me go to exercise 3. Here, if you see this input of VGG16, I just already did the very same math for every layer existing in VGG16, estimated the compute time, and the communication is all reduced with different sizes. So this workload info file is given. So I'll go to exercise 3 folder and run exercise 1. And now, because we're running actual workload on actual systems, it's taking longer time than micro benchmarking. But because this is analytical backend, it finished quite fast. And as you can see, it dumped this result here, result 1, tutorial result CSV. But again, I just copy and pasted the results here in this PPT. And this is the result. Now, as you can see, because now we are running actual workloads, now we started to see compute time, which is shown as blue on the bar, like on the bar chart and below. And this is the exposed communication time showing orange, and the total time is also being reported. And as expected, DGX uses 300 full GPU that claims to have much faster compute time than TPU. That's why DGX2 had much shorter compute time than compared to the TPU. But somehow this VGG16 workload, the communication pattern was so adverse to the DGX2's Cloud TPU architecture, which is using NVLink than using very small bandwidth InfiniBand. The exposed communication took much longer than TPU's intercore interconnects. That's why in the end, like the total training time, TPU had slightly shorter training time, training iterations. I did the very same thing with GPT-3, the famous language model. I already offered you the workload input file, and I did nothing but doing the analysis line by layer by layer, estimating the compute time, communication pattern, and the communication size is already given. And this exercise 3.2 is running that. So I will go and run the exercise 3.2 script. So now it's running GPT-3 as well. Yeah, because it's analytical, it took time, but runs very fast. And I'll show the result of running GPT-3. So for GPT-3, again, as expected, the exposed compute time shown here, DGX2 had much smaller time. And at the same time, the exposed communication time, like GPT-3's communication pattern, which is hybrid parallel, is not adverse to the GPT-2 box architecture, DGX architecture. That's why the communication time for both DGX and TPU were quite similar. So for GPT-3 kind of experiments, we can find out the DGX2 were running it much faster than TPU-like system. So till now, I'm wrapping up my section of exercise, and I'll hand over exercise 4 and the closing remarks to Tae-kyung. Thank you.